Quick revision video on polar and non-polar molecules. So we'll start with polar and non-polar bonds and then we'll move on to the molecules themselves. So polar and non-polar bonds are associated with covalent bonds, not ionic bonds. Non-polar covalent bonds are caused by atoms having same or very similar electronegativity values. So for example, the Cl-Cl covalent bond, they've got the same electronegativity values, that bond is non-polar. CH, slightly different values, electronegativity values, but they are so close that that bond is also classed as being non-polar. Polar covalent bonds, on the other hand, are caused by atoms having different electronegativity values, and the example there is HCl. So the atom with the higher electronegativity value has got the greater share of the shared electron pair in the covalent bond, and so it's going to be slightly more negative, so we show that with a delta minus sign, than the lower electronegativity value, and we show that with a delta plus sign. So in the case of HCl, the hydrogen is slightly positive and the chlorine is slightly negative. Now obviously in the exam you'll be given electronegativity values, you don't have to memorize the different values. And finally, the charge separation across a polar bond is what we call a dipole. So if we move on to molecules now, we'll start with diatomic molecules. The electron density in an entire molecule can be evenly or unevenly distributed. So in diatomic molecules like chlorine, Cl2, there's no dipole because the atoms have got the same electronegativity. So the Cl2 molecule is obviously described as being a non-polar molecule. In diatomic molecules like HCl, there is a single permanent dipole which doesn't cancel, so the HCl molecule is described as being a polar molecule. So you can see there the hydrogen has the lower electronegativity of 2.1, chlorine 3.0, and so the chlorine is going to have a greater share of the electron density, and so the dipole is going, in this case, from left to right, slightly negative at the chlorine end, slightly positive at the hydrogen end. So in non-diatomic molecules there may be different polar bonds present. The dipoles across these bonds may combine to give a larger overall dipole in the molecule, or they can cancel out if they act in equal and opposite directions. So in the case of something like this, so this is trichlorofluoromethane, we've got CCl bonds which are polar obviously because of the electronegativity difference. We've also got CF bond which is also polar. So those three CCl bonds or dipoles are all going to be identical in magnitude, operating in these directions shown by the arrows. The CF dipole is going to be greater and it's operated in this direction. So you can see that there will be an overall dipole on this molecule because these dipoles can't cancel, and so this is a polar molecule, and the dipole would be this way around, so the fluorine slightly more negative than this carbon here. So if we move on to something like this, so this is tetrafluoromethane, CF4. We've got 4 CF bonds, each with the same dipole, but they are acting in equal and opposite directions in the molecule. So effectively, they're all going to cancel out, and this is therefore a non-polar molecule. Next type of non-diatomic molecule we'll look at are those with lone pairs. So the first one is water. You can see the electronegativity values next to the atoms. So we're going to have two identical polar bonds. These OH bonds are going to be polar, and the dipole is going to be running in that direction and that direction because the oxygen's more electronegative than the hydrogen. You can see the lone pairs have caused the molecule to not be symmetrical, and so therefore these dipoles can't cancel out. Because of that, the hydrogens are slightly positive, the oxygen is slightly negative, and so the overall molecule is polar. And another example we can look at is ammonia, NH3. And again, you can see we've got three identical dipoles operating in these directions here. But again, because of that lone pair, the symmetry is broken and these can't cancel. And so we've got the hydrogens are all going to be slightly positive, the nitrogen's slightly negative, and therefore this is a polar molecule as well. So the thing to remember is molecules with one or more lone pairs on the central atom are always going to be polar, because the lone pairs break the symmetry of the molecule and the dipoles can't cancel. So we'll finish with this. 6 molecules for you to decide whether they're polar or non-polar. I would draw a shape diagram for each one, and that's going to make it very, very easy. So pause the video, have a go, and then play them when you're ready. So the BF3 molecule looks like that. It's trigonal planar, so those BF dipoles are going to be operating in that direction, and they are all going to cancel out, so this is non-polar. PF3, which looks very, very similar in terms of its formula, is actually a pyramidal molecule because phosphorus is in group 5, so there's a lone pair on the P. Obviously that breaks the symmetry of the molecule, and so therefore this is polar. SF6, well, that's an octahedral molecule. We've got the SF polar bonds, 6 of those, but they're all acting in exactly opposite directions, and so therefore they all cancel out, and this is a non-polar molecule. SO2 is a non-linear molecule due to sulfur being in group 6, and so therefore there's a lone pair on the sulfur, so straight away we know that that's going to be polar because the lone pair breaks the symmetry. CO2 on the other hand is a linear molecule because carbon's in group 4, so there's no lone pair on the central atom, and so those dipoles will cancel out, and so this is non-polar. And finally, CH2, Cl2, dichloromethane. Well, there's the shape diagram. Now, CH bond is technically classed as non-polar, but I'm going to show a very small dipole in that bond there, and then a much bigger one in the CCl bond, just to make the point that those red dipoles, there's nothing to cancel them out, and so the overall molecule will have a dipole and therefore be polar.